Good evening, everyone, and welcome to our webinar. I'm just give a few more minutes to allow attendees to join, and then we'll get started. Thank you. I can see that a number of people are still joining. So for those that are already here, we're just giving it a moment or two to allow everyone to log on, and then we'll get started. Right, I think that's a good place for us to get going. So good evening, everyone, and thank you for all attending our first technical webinar on noise and shadow flicker. My name is Ben Miller, and I'll be chairing tonight's session. Before I ask my colleagues here to introduce themselves, I wanted to run you through just how this webinar will work. Firstly, we'll have a presentation on the topics that we want to cover, and then we'll open that up to a question and answer session where all attendees will have the opportunity to ask Mark and Pete questions. During the presentation, I would ask you to provide your questions using the Q&A or chat facility that you should be able to see at the bottom of your screen. Please get those questions in as we go through the presentation, and we can have those lined up to answer at the end. I'll now hand over to colleagues to introduce themselves, starting with Pete.
Thanks, Ben. Hi, everyone. My name is Peter Rowe, and I'm a development manager at Cubico. That means effectively I'm the day-to-day project manager. Just to give you a bit of background about Cubico, we're based in Manchester. That's where our UK development team is based. So we're really passionate about this project and talking to you about it today. Cubico ourselves, we're one of the world's largest privately owned renewable energy companies. Essentially, we invest, we develop, and we operate renewable energy projects. That's both solar and also wind farms like Moor. So I'll pass you over to Mark from TNEI.
Hello, my name is Mark Tidesville. I'm a senior consultant at TNEI. We're a specialist energy and environmental consultancy. I've worked with companies since 2013, and my work involves all phases of renewable energy projects, particularly wind farms, and I've undertaken a great deal of shadow flicker and noise assessments over the years. And with that, it might be a good point to start the presentation. Okay, so thanks everyone for joining, and welcome to my presentation on noise and shadow flicker. I'll try and run through it at a fairly good pace as there's a lot to cover. So without any further ado, I think we may have covered this section already, but yeah, that's a quick overview of my experience in the industry. Just a bit of additional information on TNEI. This is a very brief snapshot of onshore wind and shadow flicker projects that we've undertaken over the years. I've probably worked on quite a few of these myself. A quick note before we get into the nitty-gritty as well. Wind farm noise in particular is one of the more complicated noise types of noise assessment that can be done for any form of development. So I've tried to strike a balance with this presentation between kind of a useful introduction without getting too technical. Appreciate that there will be some of you here today who are completely new to shadow flicker and noise, which is great, and hopefully this will be useful to you. If you do have a bit more knowledge, hopefully this is still useful as well, and you come away with some good info. So straight into shadow flicker. So shadow flicker is a phenomenon caused when moving shadows pass across a window aperture in a building where strong sunshine is present outside and provides the main source of light in the room. A moving shadow can interrupt the light, and to an occupant of the room, this can appear as if the shadow is at the light level inside is flicking on and off. Shadow flicker specifically occurs inside buildings and can lead to annoyance for building occupants. Outside of buildings, shadows cast across the ground are typically referred to as shadow throw. Generally, in the kind of outside environments, the impact on ambient light levels is much lower, and the effects of shadow throw tend to be much less. It is possible to predict when and where shadow flicker may geometrically occur based on the position of source and receiver using computer models, and I'll get into that in a bit more detail as we go along. So firstly, an example of shadow throw. This is a video clip from, I think, a site in North America, where you can see the shadows of moving turbine blades being cast across the ground near to a property. Moving shadow is visible, but it doesn't have that kind of as great an impact on the overall ambient light levels as shadow flicker within a building, which we'll get to in a second. I should note that this example, in this example, the turbine's located quite close to the property, around 300 meters, I believe, which is considerably closer than the turbines will be for Scalhorn 2. So that's shadow throw. Shadow flicker, as I say, occurs inside buildings when the moving shadow passes across a window, and you can see here the light level inside appears to flick on and off. This example was chosen as you know, and the shadow flicker video on the previous slide, as clear worst case examples, and are not intended to be representative of the kind of effects that would be present at the proposed development. And it's also worth noting that typically shadow flicker occurs nearer to sunrise and sunset, where the sun's low in the sky, and it's at a greater distance. The shadows will kind of reach further and reach properties located further away. So a quick note on shadow intensity. This diagram here is a useful example, but is perhaps on a bit of a grander scale than the proposed development. It shows the sun and the Earth in space with a single point of light considered to be the sun, and you can see how the shadows are cast by the object in front of the light source, and how the shadows become weaker outside of the kind of direct shadow and past the or into the antumbra area, where as you get further away from an object casting a shadow, the shadows become fainter and fainter as you get further away, and this will come into particular significance a couple of slides hence. So, conditions required for shadow flicker. So there are a few things that must occur. Firstly, the sun must be shining. In a clear sky, shadow flicker doesn't really occur when there's overcast weather and there aren't clear, strong shadows being cast. There must be a clear view of the wind turbine rotor from the property, unobstructed by other buildings or vegetation or structures or smaller fluctuations in landform or anything like that. The sun, turbine, and receptor all have to be in a line, which will only occur at certain times of the day and year, and there must be enough wind present so that the turbine rotor blades are moving. A few important influencing factors to consider as well include the orientation of the turbine, which can impact the duration of individual flicker events. So the diagram on the right shows a turbine facing directly on to a viewer and also kind of 90 degrees sideways. So you can imagine where the sun passes behind the turbine there, where it's facing directly on, there'll be shadows cast across the full kind of disc, the circle shown in the diagram there, of the rotors. However, under other orientations, this disc becomes considerably narrower and the individual effects occur for a much shorter duration. The intensity of shadow flicker effects can also be influenced by the proportion of the sun being obscured. So face on, there is a wider section of turbine blade to obscure the sun, and sideways, that's a much narrower, thinner potential for obstruction, which will result in weaker shadows. And as I mentioned earlier, as you move further away from the turbine, the object casting a shadow, the shadows will decrease in intensity as well. So in terms of available guidance for the assessment of shadow flicker in the UK, there is a very well-established methodology used to assess shadow flicker. Generally, effects are assessed out to a distance of 10 times the rotor diameter of the turbines. This relates directly to the diagram shown a few slides previously, where the further you get from an object, the shadows become fainter and fainter, and then it reaches a point where generally the shadows will be so faint as to not cast, or the strong shadows won't be cast, I should say. Shadows can be cast at greater distances, but typically they tend to be quite faint and diffuse. So there are a few available documents in the UK and England specifically that provide recommendations in terms of how to assess shadow flicker, and then include reference to assessing out to 10 rotor diameters. In terms of consultation, shadow flicker was included in the scoping report issued to Rochdale and Rossendale Borough Councils late last year. And a present response that hasn't been received. So in terms of the assessment of effects, as I mentioned before, the sun must be shining in clear sky, and that's what's assumed by the modelling software that we use. It also assumes a number of other worst case parameters, such as the turbines are always operating, they're always face on to each property, there are no visual blocking points, and that sensitive properties and rooms are always occupied. So the software effectively calculates the maximum theoretical amount of shadow cast that would be geometrically possible. We can, in the assessment, also consider broad corrections for factors such as average sunshine hours based on long-term measurement data to provide a more realistic prediction of total hours. So I've got a couple of examples on these slides of the kind of outputs that the software we use provides. So the first one here is an example of a shadow flicker contour plot, which is effectively a visual representation of the number of hours per year where shadows can be cast around the turbines. So you'll notice the distinct shape here. Typically there'll be a cutout to the south of the turbines anywhere in the northern hemisphere, purely as the sun will generally be located to the south, and shadows can't be cast in that direction. There's often a similar cutout to the north, just as a result of the path the sun takes through the sky. These contours, as I mentioned, they take a worst case assumption in that there's many more mitigating factors in the real world that aren't accounted for by this. However, this output can be quite useful in forming shadow flicker assessments and considering the potential of shadows to be cast near to the development. Another example here is a prediction graph, which shows months of the year along the horizontal axis and time of the day along the vertical. There are two wavy lines showing sunrise on the lower and sunrise on the upper times throughout the year, and there are a couple of coloured blobs, and apologies, the yellow colour there isn't that visible, which show predicted periods of shadow occurrence at a single receptor from two different turbines. So the green and the yellow are two separate turbines in this example. And you can see, yeah, so this allows us to kind of understand when shadow will occur at a given receptor in quite a high amount of detail. So in this specific example, we're looking at shadow flicker before sunset in January and February and October and November. So in terms of how residents are protected from shadow flicker, so shadow flicker related planning conditions can be attached to any consent, planning consent, to, in the event that shadow flicker were to impact any nearby properties these kinds of conditions typically state that a protocol document will be created for the investigation of any potential complaints, and this will be submitted to the local planning authority prior to the operation of the wind farm. So this protocol document generally is a standalone document which goes into specific detail on the how, where, and why an investigation of complaints will take place, and it will include information on potential mitigation options should they be found necessary. So in terms, in addition to residential receptors, there's also the Pennine Bridleway National Trail that passes through the site. This will be considered within our assessment, goes into planning. Shadows cast across the trail will be shadow throw compared to shadow flicker, which occurs inside buildings. Shadow throw itself is not generally assessed in most circumstances. However, it will be considered as part of our assessment for the proposed development. The assessment is yet to be finalised, so at the moment that's all the information I'm afraid I can provide on that point. So in terms of potential mitigation options for shadow flicker, one of the main options used is a system in the control software of the turbines themselves, which can shut down turbines where necessary at times where shadow flicker is predicted to occur, either based on a pre-calculated calendar of times, or there can be live software which knows where the sun, the turbine, and the receiver are, and it will calculate on the fly. The turbines, of course, have to be operating at this time for moving shadows to be cast, and there are light sensors incorporated into the turbines themselves that can tell when a certain light threshold has been exceeded, sufficient to cast strong shadows across the ground. When these conditions no longer found to be present, the turbines would start up again in order to, so the system itself is designed to offer sufficient protection to the residents while maximising generation of renewable energy. So that's a quick run through of shadow flicker. The key points are it's a well understood phenomenon. It can be calculated using software models, and where necessary, mitigation options are available. And with that, I'll move swiftly on to noise.
Thanks, Mark. Sorry, just to butt in just before you move on to noise. Thank you for that summary of shadow flicker. Just want to remind attendees to submit any questions that they have on both shadow flicker and noise, and we'll take those at the end together following the presentation. Thank you.
Thanks. So, as a brief overview of noise, well, we all know what noise is, I suppose. It's the vibration of sound perceived by the human ear. It's measured by a unit called the decibel, which is a tenth, a deci of a bell. Decibels, or dB, use a logarithmic scale, which increases exponentially. An easy way to understand this, a couple of examples here, are two equally loud sources added together. It won't be a mathematical addition. They will increase the decibel level by 3 decibels, and a 10 decibel increase in sound level generally corresponds to a perceived doubling in loudness to the human ear. In addition, you might see, particularly in some of the reports submitted to planning, dBA referred to. The A weighting scale is effectively an adjustment or weighting added to different frequencies to more accurately represent how the human ear perceives different frequencies of sound. So generally, the human ear isn't as sensitive to very low frequencies and not very high. It's more of a mid-range where human speech is present that we're more sensitive to. So this makes an adjustment to account for that. Wind farm noise in particular is its own kind of specialist subject. So noise will be admitted by the proposed development during construction, operational and decommissioning stages. Generally, noise during construction and decommissioning is quite short-term in nature, and the activities that will generate noise are usually restricted to typical daytime working hours. Construction noise assessment will be undertaken and included with the planning submission. We've got some information on that on the next slide, and of course, operational noise will be assessed in detail as well. So in terms of construction noise, in the UK, construction noise is assessed in line with British Standard 5228, which provides information on methodology, how to undertake predictions. It also provides a library of noise source data, which can be used in prediction models for estimating levels of construction noise at receptor locations. In general, where a construction noise assessment is undertaken, it's not always necessary to include a decommissioning noise assessment, as they are in many ways effectively the same thing. So where you've assessed construction noise, you have effectively assessed decommissioning noise as well. So as part of the construction noise assessment, we use specialist software to produce a 3D noise propagation model. We tend to break the entire construction down into a number of key phases where noise levels are likely to be highest, so where there'll be multiple construction activities occurring at the same time. We'll model using information provided by BS 5228. Typical items of plant that are used for each construction activity, and we'll tend to make a number of worst case assumptions. So we'll model activities occurring at the nearest point in the site to a potential receptor to take a worst case approach. So BS 5228 does provide guidance on determining appropriate noise threshold levels as well, and these are informed by background noise measurements that have been undertaken around the site. Where there is the potential for predicted noise levels to exceed these threshold levels, there are a number of best practice measures available that can be implemented to minimise impacts. Noise from construction decommissioning, as I mentioned, tends to be temporary in nature and will ultimately be controlled using an appropriately worded planning condition included in the consent. So, in terms of operational wind farm noise, the next few slides will give an overview of just an introduction to this and how it's assessed. So, in terms of noise generated by wind turbines, the main sources are aerodynamic noise generated by the blades as they move through the air, as well as a small amount of mechanical noise generated from the cell. Generally, modern turbines technology has moved on where mechanical noise has been minimised to a essentially negligible level, and the vast majority of the noise, proportion of the noise, I should say, is generated by the passage of the turbine blades through the air. So there's an image included with this slide from an acoustic camera, which uses an array of small microphones to effectively allow us to visualize where noise is coming from. And you can see here the passage of the turbine blade through the air has created a larger kind of contour blotch, you might say, compared to a quite small amount of noise from the center of the turbine in the cell. Modern wind turbines also feature a number of design elements to minimize aerodynamic noise, such as trailing edge serrations of the blades, which you might see reference to being inspired by birds' wings, the kind of serration of the feathers. This helps to kind of smooth the wind and reduce turbulent air as it comes off the blades, and also a number of other kind of additional features which can help with reducing noise caused by airflow. So in terms of assessing wind farm noise, there are a few key documents that we use in the UK. The first is XWAR 97, which is a document endorsed by the UK government, which sets out a method of establishing noise level limits which should apply to wind turbine developments. The 97 in XOR 97 does relate to the year it was released, and as things moved on in the meantime, in 2013, a supplementary document was issued by the Institute of Acoustics called the Good Practice Guide to the application of XOR 97. This provides a lot of additional information in terms of more detailed assessment methodology and how to consider larger wind turbines that are more common these days, and all sorts of information, including how to undertake measurement surveys. And this too is endorsed by the UK government. And yes, another key point here is that XOR 97 is currently being updated. This is something that's ongoing at the moment. So until an update is issued, the existing guidance remains the relevant and applicable guidance for the assessment of wind turbine noise. So as I mentioned in the previous slide, the primary aim of XOR 97 is to provide a methodology to set suitable noise limits for wind turbine developments. The way this is approached is that there are different noise limits set for daytime and nighttime periods, as generally background noise levels will be different during those times, and there'll be different levels of sensitivity. The daytime limits are designed to protect the amenity of people outside at their homes enjoying their gardens or outside areas, and nighttime limits are designed to protect against sleep disturbance for occupants inside buildings with windows open. So I've got a quote here. The authors of XOR 97, they set out to provide an indicative noise levels thought to offer a reasonable degree of protection to wind farm neighbours without placing unreasonable restrictions on wind farm development. The guidance was not designed to ensure that wind farms will not be audible anywhere in the nearby area, but instead to ensure that noise levels are kept to an acceptable degree. So, as I mentioned before, noise is measured with decibels. There are two main elements to noise to be considered, the decibel level itself, as well as noise character. So XOR 97 discusses noise character in relation to both tonal noise and amplitude modulation. Tonal noise is effectively peaks in frequency, so it might be described as I should say hum, but it says hum. Hum, a whine, or a buzz, and yeah, is due to specific frequencies of noise being raised above others. Tonal noise generally, historically, has been related to mechanical noise from the inner workings of the turbines, say gearboxes and other mechanical components. So in recent years, and generally these days, tonal noise is not a huge issue. However, XOR 97 does include a method for quantifying tonal noise and provides details of a penalty scheme to account for it should it occur. And this penalty scheme is routinely included with noise-related planning conditions. So the penalties would in effect be in addition to the total predicted noise level of the turbines, and on top of the standard level. Amplitude modulation, which is sometimes referred to as AM, is a term used to describe a variation in loudness from a noise level. So for a wind turbine, that would be maybe a swish noise as the blades turbine blades rotate and move past. This is a typical feature of wind turbine noise, which is fully considered within the assessment methodology and the guidance towards setting noise limits in XOR 97. That is generally referred to as normal AM. There is also other or excess AM that can sometimes occur above and beyond this, and where other AM occurs, it can lead to annoyance at nearby receptors. So OAM, other AM, it can be measured using a method developed by the Institute of Acoustics, which involves going out, taking acoustic measurements, recording audio files, and analysing that to quantify a level of AM from an operational development. At present, there is no government-endorsed guidance to quantify a threshold of acceptability or to assess effects. OAM can also not, at the moment, be accurately predicted based on the current available science. So, in terms of the assessment methodology for wind turbine noise, the key points are undertaking measurements of existing background noise levels at nearby properties to the proposed development. This will inform the noise level limits that would apply to the development. Different noise level limits are derived for daytime and nighttime periods. We would undertake predictions of noise at a selection of nearby sensitive receptors and compare the predicted levels against these noise limits. At that stage, where necessary, if it's found that predicted levels exceed those limits, updates to the site design can be made to ensure that noise level limits are met. And in terms of the background noise survey, so we have been out and undertaken a background noise survey at 6 locations surrounding the proposed development from, I think we started in December last year and it ran until February. So about 8 weeks in total. A number of noise monitoring locations were chosen, selected from properties identified as some of the closest to the proposed turbines. These noise measurements were undertaken in conjunction with wind measurements from a LiDAR unit, which is a remote sensing unit. It's effectively what light is to, now it's like a radar but for light. That's the best way of explaining it, I think. So wind speed and direction measurements were undertaken on the site at the same time as the noise measurements, and these were correlated for in 10-minute periods for the duration of the survey. The correlation of this data has allowed us to build up a comprehensive picture of typical background noise levels for a given wind speed or direction, which is illustrated by these graphs here. So yes, that's exactly what this presents. So there's 2 graphs on screen here, which represent a nighttime period from a measurement survey. The top graph along the horizontal axis shows wind direction, and the vertical axis relates to measured wind speed. So you can see during the survey we were able to capture quite a wide range of wind speeds and directions. Generally, we look at a wind speed range of 0 to 12 meters a second, referenced to the proposed wind turbine height and standardized down to 10 meters. In a sense, essentially, we in doing this for all developments included in the predictions, this allows a like-for-like comparison between predicted levels. The lower graph here shows wind speed, this time along the horizontal axis, and measured noise level in decibels along the vertical. So you can see on the lower graph there that during periods of low wind speed, noise levels at this location are fairly quiet. As the wind speed increases, there's more wind noise in the local environment. The background noise level increases along with that. And you can see here the the grey dots on both graphs show valid data that as we would describe it. So to go into a brief bit of detail here, there's grey dots shown in both graphs. They are the measurement data that's been kept from the survey. Blue dots in the scatter indicate periods of rainfall, which have been excluded from analysis and are shown there only for information. You can see here, particularly in the bottom graph, that the periods of rainfall typically have led to increased noise levels, and that is one of the key reasons why we would and do remove those from the analysis. There's also a number of red points scattered throughout the data there. These relate to other exclusions made for atypical periods identified through analysis of the data. So this might relate to an unexpected spike in noise level that can't be explained and is attributed to maybe activity in the local area, or perhaps periods of snowfall, particularly where there's snow present on the ground. This is excluded from our analysis as where rainfall might increase background noise levels. Basically, snowfall can, while falling, depending on the kind of precipitation, it can increase noise levels, but while snow is present on the ground, it can initially reduce noise levels where there's fresh soft snow, and in the event that this freezes, this can increase noise levels as it crusts over to a hard shell. So there's lots of things that can impact this data, and as we're looking for the typical background noise levels for a location, we remove anything that might distract from that. So finally, there is a black line drawn through the center of the data representing the average noise level from all of the measured data during the survey for this location. So now that we have the background noise level identified, this is shown on its own on the graph here, the same as the lower graph on the previous slide. Wind speed along the horizontal axis and noise level in decibels on the vertical. In this example, so here I've added a noise level limit. So this will be a daytime noise level limit. There are two key elements to consider here. The first is a fixed lower limit. So for daytime periods, this is typically set at 35 decibels. And the other element is an increase of 5 decibels over the measured background noise levels. So typically, you'll find this is a common approach to ETSI 97 noise level limits. You'll have a fixed lower limit, and at higher wind speeds, this will be overtaken by the elements based on background noise levels. So finally, the third string to the bow here are predicted noise levels from our wind farm, shown in blue on this line here. It's worth noting here that the middle of the wind speed range is often the key area for these assessments, as it often corresponds with the period where predictions are closest to the limits, as in this example here. At lower wind speeds, turbine noise typically is quite low and remains below the fixed lower limit, and at higher wind speeds, the background noise level is higher and will mask turbine noise. Cumulative wind farm noise will form an integral part of our noise assessment. So predictions will be made from all proposed, consented, and particularly operational wind turbine developments in the immediate area. The IOA GPG does include very detailed guidance on the assessment of cumulative noise, which will be followed as part of the noise assessments submitted into planning. So once we have the measure background noise levels, the noise level limits, we need to choose a number of noise assessment locations at which to make predictions. Generally, not every single property around a wind farm development will be assessed, as in some cases there are simply too many to do so. But the typical approach is to pick a number of representative locations. These will generally be the nearest properties to the proposed wind farm, where predictions of wind turbine noise will be highest. At further distances, noise from the turbines will be lower, so where the noise level limits are met at the nearest property, it can be assumed that they will also be met at a more distant property. In addition to assessing noise at residential receptors, noise across the Pennine Bridleway National Trail will also be considered as part of the operational noise assessment. So how are residents protected? Well, noise level limits that as I've been over in the previous few slides, form a key part of this. Noise from the operation of the wind farm needs to meet these limits. The noise level limits will typically form part of a noise-related planning condition that will be attached to any planning consent, and this will include consideration of tonal noise. These kind of conditions will typically state that in the event of complaint related to noise, the operator of the wind farm will appoint an independent consultant to undertake compliance monitoring. So typically, this would be a similar process to the background noise survey, where measurement equipment is installed at properties near to the wind farm to measure the noise being produced and ensure that it meets the level limits applied. In the event that noise is found to be an exceedance of the limits, the operator of the wind farm would need to ensure that the limits are met. This can involve operating the turbines in alternate operational modes to reduce noise. This will typically come at the expense of reducing the generation of energy as well. In addition to this, the local planning authority would be able to call upon its existing statutory nuisance powers where required. These powers can be used, if required, to resolve complaints regarding amplitude modulation should they occur. So, in summary, shadow flicker is a phenomenon caused by the passage of moving shadows across windows in properties. Shadow throw, on the other hand, is where moving shadows pass over the ground outside. An assessment will be undertaken to quantify potential shadow flicker effects at nearby sensitive properties, as well as sections of the Pennine Bridleway which pass near to the proposed development. And in terms of noise, noise will be produced as part of the construction, operation and decommissioning of the proposed development. However, noise from the proposed development will be assessed in line with all current good practice and controlled through the use of noise-related planning conditions. Okay, and that, I believe, is the end of my presentation.
Thank you very much, Mark, and thank you to attendees who've been submitting their questions throughout that. We've got plenty to get through. So the first one is with regard to whether these slides and this webinar will be available after this. And yes, everything is being recorded and will be made available on our website, and that goes the same for the wider webinars that we're hosting next week and the week after. The Q&A, as we've got through, as I mentioned, we've had a lot of questions through. A lot of these have been submitted anonymously, and if that's the case, then they'll be dealt with in the statement of community involvement if we don't get through them this evening. If you would like to ask a specific question and get an answer direct, you can email the project team and or give us a call or submit a feedback form online. I'll provide those details before we finish. The first question, Pete, I think you're probably the best person to take this one. How can you accurately assess both shadow and noise issues when you've not confirmed turbine specification, size, position, etc.?
Yeah, happy to say that, Ben. I suppose at this stage we're still at a sort of pre-planning stage. So we're still, well, Mark in particular is sort of working very hard in the background in terms of undertaking all of these assessment works, which will then be set out completely in the planning application. As part of this consultation, the way out it differs from the first one was if attendees had seen the details we published back in November, it was very high level in the sense that we were identifying a broad area of search almost for the wind farm. What we've done in this consultation is that we've actually provided specific locations on an OS base, so you can see the exact location where turbines will be situated. And then what we're doing alongside that is we've said that we're looking at turbines up to 180 meters. It's entirely normal with wind farm developments that you don't actually need to know the exact turbine specification at the time that we submit a planning application. Essentially, you apply. It's called the Rochdale envelope approach. So essentially, what we do is we set worst case parameters for the tip height of the turbine. And then all of that information allows Mark then to undertake the relevant surveys that they do in terms of noise and shadow flicker. But Mark, I don't know if there's anything that if I've done that down too much, you might want to jump into a bit more of the specifics.
No, I think that covered it very well. Anything further to add?
Thank you. Another question we've had more generally is, I'll just read it verbatim. I believe there is an unadopted recommendation that was supported by the House of Lords that no turbines of this size should be within 3 kilometres of any properties. Are you adhering to that recommendation? And if not, why not? So I think it's just worth reflecting on what this actually is. I believe this was an attempt by a private member of the House of Lords, so not a government minister, to bring forward a private member's bill a couple of times in the early part of the last decade. In both occasions, I believe that bill didn't progress past its first stage, which is the first reading in the House of Lords, didn't make it into the Commons, so it never became law. As I say, it was a private member's bill attempt rather than government regulation. So it's not actually a formal recommendation.
Cool, but do you want me to sort of jump in with a bit more on that as well?
Sure.
I mean, yeah, I think that is the factual position regarding the private members bill. It was obviously brought forward a very long time ago. You're sort of looking at best part of 15 years ago, aren't you? And it didn't proceed to law. I think what I would say from a planning perspective is that the planning system gives local planning authorities the tools that they need to assess impacts like visual amenity, noise, shadow flicker, all on a case-by-case basis. And it's not necessary to apply a fixed distance that wouldn't reflect local context. So instead, what we're doing is we're undertaking very detailed assessments using sort of industry best practice and guidance. And that makes sure that each of the turbines are sensitively sited and all of the potential effects are fully understood and mitigated. And that just means that instead of just using a one size fits all, we're sort of very much looking at that local context. Yeah, so I think that answers it. I mean, the other point as well is that the distances that we're looking for set-offs are akin to those that have been used over the last decade on wind farms in Scotland as well. So we're not doing anything here that's novel or something that sort of counters the sort of accepted best practice across the UK.
Thanks, Pete. What is the 10 times the rotor diameter distance in this case, and are there any properties within that distance? Mark, is that something you're able to answer?
Yeah, for the purposes of the assessment, we're considering a turbine with a rotor diameter of around 150 meters. So 10 times that would be 1.5 kilometers. I believe there are some properties within that distance of the turbines, and where they are, they'll be considered, in detail in the assessment. They'll be used as assessment locations, and we'll be able to predict and estimate the level of effects that may occur there, and any requirement for mitigation.
Thanks, Mark. Will you be assessing shadow throw impact on all footpaths, bridleways, and national trails, etc.?
That's certainly something we can look into. We have been looking so far. We've been focusing on the national trail, Pennine Bridleway, that runs throughout the site. But due to its significance, we can consider other rights of way throughout the site as well.
Thank you. An attendee's asked, my understanding is that noise duration is as important as noise level. Is that correct? And will you also assess in terms of duration?
Yes, we will. However, the assessments that we undertake do take a number of worst case assumptions. So the predictions assume that the receptors are downwind of the wind farm at all times. For much of the time, particularly as houses are located at different orientations around the wind farm, it's likely that downwind conditions won't be present for much or perhaps the majority of the time. So while we do, and the methodology that we follow does consider the duration of effects, we tend to take a fairly worst case approach when assessing noise. So yeah, we tend to go a bit more worst case than strictly necessary in that regard.
Well, thank you. Another question. So when you say that shadow throw is not usually a problem at distances greater than 10 times the rotor blade size, as it is faint, can you please clarify what you mean by that? Horses are perturbed by any moving obstacle, and so has any research been done that this is true for the horse's vision rather than human vision? Also, when is it expected that the effect of shadow throw on the Pennine Bridleway will be completed, and will it be shared with the community?
The assessment of shadow throw and shadow flicker will be included as part of the planning submission. So I'd defer to Pete on that. In terms of the 10 rotor diameter assessment area, this is based on a number of factors, but largely the typical dimensions of a turbine blade and the kind of width of the blade itself as a factor of the length. That generally relates to the size of the object casting the shadow in front of the sun. So as a general rule, beyond 10 times the rotor diameter, the width of the blade itself to the receptor will be sufficiently narrow or small enough as to not block out the whole sun, and at that point strong shadows are no longer cast. Just weaker, more diffuse shadows that have a lower effect on the light levels in the environment. I'm not aware of any studies that have been undertaken specifically on the response of horses to shadow effects beyond this distance. I'm afraid I'm not aware of any specific studies that have been undertaken in that regard.
Oh,
John, Ben, you want me to jump in, just give a bit more on that one? I think I would say just sort of we take the impacts on the bridleway and also horses in general, and also the impacts on the sort of equine community and the economic benefit they bring really seriously. So I think we might have some members on from the local bridleway association at the moment. So I think would say welcome a further meeting and conversation with you, really, and to take you through this and the process that we're taking, bring you on the journey of assessment that we're currently on. In terms of asking the specific question of when that information will be available, it will be when the planning application is published. So we will make that available in two places. It will go on both of the local authority websites, as would usually happen with any planning application, but we'll also make a copy of it available on our website in the resources section. So all of that will be publicly available and open to scrutiny, and there will be another period of public consultation that will be organised by Rosendale and Rochdale as the local planning authorities.
Thank you, Pete and Mark. We've had two questions on ETSU 97. The first one is, I understand that it's out of date, as I think you referenced in your presentation, Mark. But there's nothing else yet in place. How do you deal with the challenges that are out there in terms of the obsolescence and the more recent regulations being discussed? Will you consider more recent recommendations that are not yet passed into regulation and/or law?
At the moment, I would not say that ETSU 97 is out of date or obsolete. Until such time as an update is available, it remains the endorsed guidance for the assessment of wind turbine noise in the UK. Coupled, as I mentioned in my presentation, obviously the standard is fairly old at this point. However, it was updated in 2013 to account for more modern practices and more modern scales of wind turbine as part, well, with the IOA GPG. And yeah, until such time as a replacement is available, they remain the appropriate documents to follow in terms of assessment of wind farm noise.
Thank you. Some further questions on noise. Where does low frequency sound come into the noise assessment process?
So low frequency noise is something that's raised quite frequently in relation to wind farms. It won't be something that it's not something we're intending to specifically assess as part of the noise assessment. However, it will be considered within it. Most recently, there was a report published by WSP in 2023 called the Review of Noise Guidance for Onshore Wind. The report did consider low frequency noise in detail, and I've got a couple of quotes handy here. It concluded that overall findings from the existing evidence base indicate that infrasound, low frequency noise from wind turbines at typical exposure levels has no direct adverse effects on physical or mental health, and reported symptoms of ill health are more likely to be psychogenic in origin. Following this, the publication of the WSP report, there was further studies undertaken in, I believe, last year in Australia, where a study was undertaken to test the effects of exposure to infrasound over a period of 72 hours on subjects. That study concluded that findings did not support the idea that infrasound causes any wind turbine syndrome, which is kind of a negative physiological effect related to wind turbine noise. High level but inaudible infrasound did not appear to perturb any psychological or physiological measure tested in these study parameters. So in brief summary, the currently available science suggests that low frequency noise associated with wind turbines and wind farms is not there's no evidence to show that it causes any negative effects.
Ben, just on that, just a quick observation today that Mark's helpfully referred to a couple of documents and also quotes which maybe attendees wouldn't have been able to sort of catch. So I think maybe in the notes underneath we can give a URL link if that's available, Mark, and then we can just highlight those sections that you've referred to, just so make sure.
Absolutely, of course.
Yeah, of course, and we can make those available on the website underneath the recording as well, so that people have that context if they're viewing it online. I am mindful of time as we're approaching 7 o'clock. So I've got time for one more question. I know that there are a number of questions that we haven't managed to get to, but as I said at the beginning of the Q&A session, these will be dealt with in the statement of community involvement that will accompany the planning application. So all questions will be answered. And if you want a more direct response ahead of that, please do email the team. So the final question that I'll ask is, do you factor in additional noise from third parties as a result of the development, e.g. motorbikes and antisocial behaviour?
That kind of noise isn't typically included as part of a operational wind turbine noise assessment due to the nature of the noise produced. The assessment methodology is very specific and relates to different noise levels at different wind speeds. Where there is the potential for additional noise due to antisocial behaviour on the development itself, that could be controlled through existing powers of the council, such as the statutory nuisance powers mentioned earlier in the presentation there, as a separate issue.
That's great. Thanks, Mark. And that brings our webinar this evening to a close. I want to thank Mark and Pete for giving up their time this evening, and thank you to all attendees for giving up your evening to come and listen to us and to ask the questions that you have. Community consultation is really important to Cubico and to the wider project team, and we're grateful that attendees have participated in really good numbers. This webinar tonight is one of a number of events that form part of the wider community consultation programme. Up next, on Thursday the 17th of April, we're holding another technical webinar on protecting peatlands and moorland restoration. As it has tonight, that will start at 6 p.m. And if you haven't already registered, you can do so on our website. In addition to the exhibitions that have already taken place, we have two more coming up after the Easter long weekend. On Wednesday, the 23rd of April, we'll be at Cap Community Hall. And on Thursday, the 24th of April, we'll be at Edenfield Community Centre. Again, further details of those are on our website. And then finally, our last technical webinar on the subject of access and infrastructure will take place on Friday, the 25th of April at 6 p.m. And again, you can register for that on our website. Our consultation remains open until the 29th of April, and I would encourage everyone who hasn't already to visit our website and provide feedback using the form on there. You can also contact the team by email, scoutmore2@havingyoursay.co.uk, or by phone on 0333 358 0502. Those details are also available on our website. There's nothing left for me to say other than thank you again for attending tonight, and I hope everyone has a pleasant evening. Thank you and good night.
Thanks, everyone.
Thanks.